In this problem, we're going to use a differential equation approach to find v0 of t for t greater than 0, and we're going to plot the response. This is a first order circuit. We only have one energy storage element, the capacitor. We have DC sources, so we know that our solution is going to be of the form v0 of t is k1 plus k2 e to the minus t over tau. Now to start our solution, let's draw the circuit at t equals 0 minus. We're going to assume the circuit's in steady state, so our capacitor will replace it with an open circuit. Here's our circuit at t equals 0 minus. The capacitor's been replaced by an open circuit, and we need to solve for the capacitor voltage. And if we look at this circuit, for instance, it's really circuit has 3 nodes. If we pick this one as a reference, we have a node voltage here which is known, and we have another one here which is V0 0 minus. So let's apply KCL to this top node to come up with a nodal equation. So for instance, if we do KCL at the top node, we get V0 0 minus over 6K. For instance, that could be the current here. Then we'd have V0 minus over 6K would be the current here. Then we would have V0 of 0 minus 9 over 6K. That would be the current in this direction, and that's equal to 2 milliamps. So this current's leaving, this current's leaving, this current's leaving. So we have the sum of the currents leaving equal to the sum of the currents entering. And if we solve, we get V0 of 0 minus equal to 7 volts. So there's our initial value of our capacitor voltage. Now let's take and draw the circuit for t greater than 0. Here's our circuit, and really it's a single node pair circuit. So we know, for instance, we've got a reference node, and then we can apply KCL at the top node. So when we do that, we'll have 2.5 times 10 to the minus 6 dV0 dt. That's the current through the capacitor. Then we'll have V0 of t over 6K. That's the current through the resistor. And that's equal to 2 milliamps. Now, let's divide through by the 2.5 times 10 to the minus 6. So we have dV0 dt plus 66.67 V0 of t, and that's equal to 800. So we went around there and cleaned up the terms. We know our solution is K1 plus K2 e to the minus t over tau. So now let's plug it in. So now we have the derivative of K1 plus K2 e to the minus t over tau plus 66.67 times K1 plus K2 e to the minus t over tau equal to 800. And if we do the operations here, we have minus 1 over tau K2 e to the minus t over tau plus 66.67 K1 plus 66.67 K2 e to the minus t over tau equal to 800. Now if we think about what an equal sign means, for instance, everything on the left's got to equal everything on the right. And if we look at our equation here, here's a term. These two terms don't involve e to the minus t over tau. So one thing we can conclude from this is that 66.67 K1 has to equal 800. And the other thing that we can conclude, the terms here that are multiplied by e to the minus t over tau, we have minus 1 over tau K2 plus 66.67 K2 has to equal 0. So for instance, these terms cancel out. And if we solve for our values here, we have K1 is 800 divided by 66.67, which is 12. And we notice that 1 over tau is 66.67. So then tau is 1 over 66.67, or 0.015 seconds. So now we know that V0 of t is 12 plus K2 e to the minus t divided by 0.015. And we still need to calculate K2. We can do that because we know that V0 of 0 minus equals V0 of 0 plus is 7. And that's 12 plus K2. So then K2 has to equal minus 5. So then our solution is V0 of t is 12 minus 5 e to the minus t divided by 0.015 volts. Now if we want to plot that, our voltage would come along at 7. The switch would move, and it's headed toward a final value of 12. So then it would look something like that. And if we think real quick and say, well, does that 12 make sense? If we go back to this circuit real quick, once this switch is opened, when you reach steady state, this capacitor is going to be an open. So the 2 milliamps is going to flow through the 6K, which is going to give us the 12 volts.